Hey guys, Mr. Smith here, and we're shooting a video about rates of change. Specifically, we're talking about today average rates of change and how they connect to the slopes of secants on a graph. So, let's get started. So, the reason we are looking at rates of change, a major reason is it introduces some ideas that help you in the calculus course. Um, um, because everything in the world is constantly changing, and we want to be able to analyze how things change, what rate of things changing, so we can like make predictions and make models. So, for example, like a person's height and mass changes from birth to adulthood, distance a car travels changes according to its speed, and um, back in your grade 9 course, maybe you did average speed problems where you found like the slope of a distance time graph and it gave you average speed. But in reality, like cars aren't moving at a constant speed the whole time. They're constantly speeding up and slowing down, and we need to develop tools to be able to handle these kinds of functions where it's not necessarily just obvious what the rate of change is. It's not just linear. We need to be able to handle when things are constantly fluctuating. I've got an example that's relevant to me. So my son is a type 1 diabetic, and so we have a device that monitors his glucose levels. So it's like a little mini patch on his arm, and it gives us an update every 5 minutes on his glucose levels. So not only can I see what they are, which is important, but I can see if he's having a really big drop. Like you can see over the course of this time, this is just a nice gradual drop until maybe he needs a snack or some food. But sometimes he can have a big rapid drop like so, where the rate of change of his blood glucose levels over time is a steep drop, and um, those times when that rate of change is really big, I need to know those too, so that I can intercept those big drops with like a quick snack or just getting him to rest for a second before he gets into kind of semi dangerously low levels. So rates of change to me are very applicable today. Well, let's actually just talk about. I've been throwing this word around, rate of change. You guys would have talked about rates of change in your grade 9 math course. A rate of change is a measure of how quickly one quantity, the dependent variable, changes with respect to another quantity, the independent variable. Now I'm just going to do a little bit of scratching over here. So a little bit of chicken scratch. Rate of change. Oh, tablet, don't be acting up today. Um, so this should kind of look familiar from your grade 9 course. So to get a rate of change, it was like how is one variable, the dependent variable, usually y, changing with respect to the independent variable. And then as you guys proceeded through grade 9, you connected this to the slope of a graph, and you developed your slope formula. M equals rise, the slope is rise over run, which is change in y over change in x, and eventually you developed your slope formula. So like in grade 9, you talked about rates of change, but then you made that connection to slope, and then everything was a slope, and you stopped talking about rates of change so much. Um, we're going to make more connections between rates of change and slope today as well. We are talking specifically about average rates of change. So there are two types of rates of change: average and instantaneous. Uh, Today, we're looking at average rates of change, and in our final lesson for this unit, we'll talk about instantaneous rates of change. An average rate of change is the change that takes place over an interval. So, for example, with Bryden, and I'll just erase some of the markings on here. If I could think of his his monitor gives me a reading every 5 minutes. But I could think of it as like a smooth function. I'm just going to put a little bit of a line to that curve. So maybe from 7 to 8 a.m. I would be like wondering, well, hey, like how did Bryden's glucose levels change from 7 to 8 a.m. And I would look at, well, how did the his sugar levels change over time? So I'm just gonna find green's always a horrible choice. So from 7 a.m. to 8 a.m. It's like going up here. I would look at, okay, it looks like he went up 10, and the units for his blood sugar level are called millimoles, and then in the time it was 1 hour. So I could say, hey, for from 7 to 8 a.m., his blood sugar level was changing at a rate of 10 millimoles per hour, or something like that, right? Whereas, sometimes I might be concerned with, well, tell me exactly right now how the rate of change of his sugar levels, how is it changing? So I might be interested to know at a single point of time, like, well, how is his blood sugar levels changing? And what we're going to deal with today is how to find the rate of change over an interval, like the first guy here. And then tomorrow, we'll figure out, well, how can you find or estimate a rate of change, an instantaneous rate of change at a single point of time? Because you can't do delta y over delta x, change in y over change in x. You can't do this if you don't have 2 points, right? Because you need an interval, a change. So, but yeah, that's for tomorrow. But that's average rate of change over an interval. And what we're talking about today is nothing too overwhelming, just how to find an average rate of change from a variety of kind of starting points. So here's a very simple example. This is just like review something you might have seen in your grade 9 course. A typical grade 9 course would ask, like, hey, what's the rate of change in this question? And then interpret what that means. In this case, the rate of change of distance with respect to time, we know that's average velocity. So for this problem, the average velocity, it's a rate of change. It's a rate of change with distance over time, distance being the dependent variable. So change in distance over change in time. Remember, delta is just the word, just means change. So this is change in distance all over change in time. It's just that Greek letter delta is just a nice way of saying change, minimizes your writing. And here we have the change in distance was 420 kilometers. And this happened over a course of 4 hours. And 420 divided by 4 is 105. And the units of rate of change here would be kilometers per hour. And so this is like a typical rate of change question from your grade 9 course. Find the rate of change, interpret what it means. Here it gives you the average velocity. But again, we know, like, this car is not traveling at 105 kilometers per hour constantly. This car would be speeding up and slowing down, like maybe stopping for a while to get some gas or something. Like, that's not a realistic graph of what it might look like, but you get the idea. The speeds would be constantly changing. So this is how we can find an average rate of change. Change in dependent variable divided by change in the independent variable. So what are the connections to slope? Again, something you guys would have developed in your grade 9 course. So I've given you kind of a visual here that we'll play along with. So the average rate of change between 2 points, it corresponds to the slope of a secant between 2 points. So in your grade 10 math course, you guys were introduced to the idea of a secant. We've got one visualized there. I'll just draw another one here. A secant is a line segment, a line that joins two distinct points on a graph. So that's what a secant looks like. And in that visual there, a secant is being drawn between points P1 and P2 in orange. So if this was a function modeling something I wanted to find a rate of change of, so I would do delta y over delta x using my 2 points. And you can see that the delta y over delta x corresponds to the rise and the run of the secant. So this average rate of change we've been talking about, it connects to slope. It's the slope of this secant in orange. And we would determine the average rate of change in this way. And again, we're still kind of in like almost review mode. You guys will be glad that today the math today not so heavy. Just reviewing some lingo, kind of getting you set up for the calculus course. It's a nice little interlude from polynomial functions. So average rate of change in the dependent variable over the change in the independent variable. Remember, this just means change in y divided by the change in x. And to get the change in y from one point to another, P1 to P2, you just subtract the y values. And think back to your grade 9 math course when you first saw this formula. This is the slope formula. This is literally the slope of the secant. So big idea so far, average rate of change is how the dependent variable is changing with respect to the independent variable, and it's connected to the slope of the secant joining those 2 points. And what we're going to do for the remainder of this video lesson is we're going to find rates of change in a variety of ways. So the first way we're going to do that is from a graph. Literally, this might have been a question you did in your grade 9 course. Nothing too crazy. We've got a little visual here showing us how the amount of money in a bank account is changing over time over the period of 1 year or 12 months. And we're going to find 3 rates of change and just kind of talk about what they mean. So I've got a little small visual up in the top there, just so I don't have to keep going back and forth. You guys will have this on your page though. Maybe let's do the first one together, and then maybe you can do the second two, and then you can do the usual pause and unpause when you're ready. So we're calculating the average rate of change. Now, just because like I'm kind of limited for space here, I'm just going to put average rate of change just to maximize my use of space. So to find the average rate of change, we're finding the change in the dependent variable. So it's the change in the amount in our bank account divided by the change in time. And I can see that at 0 months, I had 500. At 5 months, I had, careful here, it looks like 1,000. And so what's the change? So I'm not trying to insult anyone's intelligence. I know you guys could do this with mental math, but I'm just showing how the process works. And yeah, hopefully this is mainly a review for you guys. But 1,000 minus 500, that's the change in the amount between those 2 points. The change in time, 5 months minus 0 points. Guys, we're literally just finding the slope of that line segment. So we get 500 over 5. 100. And the interpretation there is our bank account is climbing at $100 per month. And maybe I'll just pop in here that it's increasing. Let's look at the average rate of change between months 5 and 8. So again, that's not how we write points. Fully expect you guys be able to do this with mental math, just visualizing the process. 8 1,000. So the average rate of change. Now it's still a change in amount. Maybe just to save some room, let's call amount A and let's call time T, because then I can write this more concisely as delta A over delta T. I like that idea. Calling a little audible on the fly there. Yeah, that'll save us some writing. Okay, what's the change in the amount from 5 to 8 months? Well, it's 0, right? It's 1,000. It was 1,000, and now it's 1,000. It is 1,000. It was 1,000, and then that's the change in time, 8 minus 5. So it changed $0 in 3 months. 0 divided by 3 is 0. And, this makes a lot of sense. We get $0 per month, which just means no change, right? And the slope of the slope of a horizontal line is 0. So everything is connecting to slope here. And 8 to 12, let's do that. So 12, 200 is that final point. So the average rate of change between these 2 months, I'll just keep using delta A over delta T, change in amount over change in time. Okay, so the final amount was $200. The initial amount was $1,000. And this happened over 12 minus 8, 4 months. So we get minus 800 divided by 4. And this is the difference here. So rates of change can be negative too, which makes sense because slopes can be negative, right? So here we get negative 200, which just means decreasing. Our bank account is decreasing $200. We'll squeeze this in here per month. Nothing new here, guys. We're just connecting rates of change to slope. Again, we're making these connections now because they're very important for your calculus course. But hopefully you're just finding this to be a little spot of review. All right, so you can, if the graph is detailed enough, you can read off the change in the dependent variable and the independent variable, and you can find the average rate of change. And we're making that connection to slope. The slope of this first line segment is 100, increasing on $100 a month. The slope of the second line segment was 0, bank account staying the same. The slope of the last one was negative. The bank account is decreasing. So average rates of change can be positive, 0, or negative. Let's continue. All right, we can also find rates of change from a table of values. I mean, it's not rocket science. In the last one, to calculate the rates of change, we picked those values from the graph. And in this case, they're not in a graph for us. They're just listed in a table. So we can just pick off those values. So what we're going to do in this case, we've got a bacterial culture, and we're testing an antibacterial spray on it. So over time, the amount of bacteria is going to decrease and decrease because we sprayed it with some antibacterial spray. We're going to determine the average rate of change of the number of bacteria over the entire period of time shown in the table, so from 0 to 7 minutes. So essentially, we're finding how many bacteria are going to be killed off every minute. And our 2 points we're going to be using are, so this question is going from 0,800 to 737. What's the rate of change, right? This is like I'm going to make a connection here from that point to that point. I'm just going to draw a dashed line representing the secant. And I'm just going to add this in, just improvising on the fly. The average rate of change is the slope of this secant. Just making some connections there. Math-wise, guys, nothing crazy here. Arguably, you guys could have done this after your grade 9 math course. So let's do it. So the average rate of change, it's the change in the bacteria population over the change in time. 37 minus 800 represents the change in bacteria population. 7 minus 0, the change in time. And we get 763 over 7, which is divisible by 7. Oh boy, I'm going to get in trouble here. That's 109, I believe. Actually, excuse me, that's negative 763. It is 109. It equals negative 109. What's the interpretation of this? So again, that's the slope of the secant. It's the average rate of change. And what's the interpretation? On average, 109. Um, Interesting announcement there. I'm actually just going to pause my video and go do that. All right, and we're back. The joys of shooting your video lessons during school hours. So, on average, when 109 bacteria die off each minute. So, you can always calculate a rate of change, even if you don't have a graph to calculate the slope. It's just like you literally use the ordered pairs. So nothing too crazy going on there. You can find a rate of change from a table. Lastly, and this may be the one thing that you didn't do in your grade 9 course, is finding rate of change from an equation. And it's not really too bad to do. It's just that, in the previous examples, like from the graph, you can pick off the 2 points. In the table of values, again, you can just read off the 2 points. When you have an equation and you're asked for a rate of change over a certain interval for the independent variable, you just have to kind of get the 2 points. You have to get those points yourself. So we have maybe just a bit of work to do off to the side. We need to know if we want to find the average rate of change of height of the ball, the change in height over change in time. We actually need to calculate what the heights are at each of these times here. So I'm just going to, just before I do any work with the rate of change, just going to find the height at 0. This one's not too bad. It's always nice when you're just plugging in 0, 14 plus 1. And you guys can work that on your calculators, but we do just get 1. And then we need to know the height after 0.5 seconds. I'm going to have to dig my calculator out here. I definitely will. And I'm not gonna like show a bunch of steps here. I'm just gonna just slam that out on my calculator. Minus 4.9 times 0.5 squared plus, that would be 7 plus 1, 6.775. All right, so after 0 seconds, we are 1 meter above the ground. After 0.5 seconds, we are 0.677 meters off the ground. And if you'd like, you can write down what kind of points these correspond to. This would correspond to the point 0.1, and this would correspond to the point 0.5, 6.775. And now we can proceed like we did in the previous examples. So we now have the 2 points. We can see the change in the independent variable and the change in the dependent variable. So let's do it. Average rate of change equals the change in height over change in time. Now I'm going to be naughty here and just do a couple equal signs on one line. So just a reminder of what we did, we're finding the change in height. That means the height after 0.5 seconds minus the height after 0 seconds divided by the change in time from 0.5 to 0. And now we have those values, right? We did them off to the side. So 6.775 minus 1 over 0.5 minus 0. I should be able to do that with mental math. 5.775, we're multiplying that by 2. I think it's 13.5, but I don't know. I'm just 775 divided by 0.5. 13.55, close enough. And the interpretation of this, right, is that this is 13.55 meters every second. It's like the average speed of the football during this time. We know the football is not moving at a constant speed, but over this time interval, that was the change. Now, I think did I make an error here? So 6.775. Something seems off here. I'm gonna pause the video where I sort that out. All right, and we're back. And this is one of those situations where you're probably screaming at your computer screen. I made a small error here. I did 6 points. I forgot to subtract one. This actually just gives you 11.55. So good thing. Nothing major needs fixed. 11.55 and 11.55. And because it's positive, we know our football is moving up. Now let's look at the rate of change for 2 to 2.5. So we're going to need to. Do I have room? Yeah. You know what? I'm just going to do all the interpretation on this slide, and then we'll make a big visual on the next slide. So in the same way, to find the average rate of change, we're going to need the height at 2.5 seconds, and we're going to need the height at 2 seconds. So let's just do those now. Don't know why I did that one first. The height at 2, the height at 2.5, and we'll slam those out. So minus 4.9 times 2 squared. I'll try to minimize the mental math, but sometimes, guys, I just can't help myself. I just want to do mental math. But yeah, let's see what this one is. So negative 4.9, that'll be times 4 plus 28 plus 1. So I got 9.4 meters for the height after 2 seconds. And after 2.5 seconds, as we're doing this, like, hopefully you guys are convinced, like, finding average rates of change, nothing too crazy. It's all stuff, like, honestly, I could teach a grade 10 course this exact same lesson, and they could do it. So it's just a nice change of pace from what we've been doing. But yeah, the reason we're doing this, guys, that we're getting you guys ready for calculus, and we might pull this idea of an average rate of change out later on in the year as well. All right, and then 5.375. So let's find the average rate of change over this time interval from 2 to 2.5 seconds. So it's change in height over change in time. That means we're finding the height after 2.5 seconds, and we're subtracting the height after 2 seconds, all over 2.5 minus 2, and we have those values. So 5.375 minus 9.4 over 2.5 minus 2. And I'm just going to do all this at once, just to save some space. About 1.5. All right, so in this case, we get a negative rate of change, negative 8.05. And our interpretation here is the heights in meters, the times in seconds. This is 8.55 meters per second, but the negative implies it's moving down. Its height is decreasing. 8.05, excuse me. And I've got a little visual of this on the next page here. So again, if you need to get this down, you can just pause. But yeah, here we go. So in our first question, when we found the rate of change from 0 to 0.5, remember, guys, what we were finding, at least if you connect it to the graph, is the slope of the secant between these two guys, right? If you want to label this on your, I'm not sure if you guys have this visual, but if you want to get it copied down, you can. So we started at 0, 1, and we found out that after 0.5 seconds, our height was 6.755, 775, excuse me. And we can see that, if the red function marks the path of the ball, that during that time, its height was increasing. So the rate of change, the average rate of change was positive, and it was 11.55 meters per second moving up. But our negative answer in the last bit makes sense too, because at point C, we were at 9.4 meters. Just erase that there. After 2 seconds, we are at 9.4 meters. And then after 2.5 seconds, we drop down to whatever it was, 5.375. During that time, the height is decreasing. The secant between C and D has a negative slope, and it makes a lot of sense about why we got a negative average rate of change there. So the rate of change gave us the speed of the football over those time intervals, and the sign told us whether it was increasing or decreasing. And that's what you guys need to be able to do coming out of this lesson. Can you find a rate of change from a graph, provided enough info you can read off the values, a table of values, or if you have the equation, can you generate those dependent variable values yourself and then just find the average rate of change? And we also made some connections between average rate of change to the slope of a secant. In our next lesson, we'll talk about how we can deal with instantaneous rates of change. Remember, this would be like me asking, hey, I know that from 7 a.m. to 8 a.m., Brendan's blood sugar went up by 10 millimoles per hour. But what about exactly at, say, 9 a.m.? I want to know exactly, hey, at what rate is Brendan's blood sugar dropping? How do we find a rate of change for a single point? We'll talk about how to do that. Now you guys have some practice to work on. And this is the end of lesson 6. We got one more lesson in our unit, and we'll have wrapped up our first unit on polynomial functions. That's it for me, guys. Hope you're having a good day. Stay well. We'll see you soon.